Okay, let's move on to part two of this video. This is about reflections, not my own personal reflections on life, but reflections of a voltage when it reaches the load. Now, I've given away what's going to happen. I said in the last video that we've got a wave moving down from the generator to the source. Let me go back to my drawings here, right? Where the moment that this switch closes at t equals 0, this voltage and its internal resistance is going to create a voltage wave, which starts out at the source side and works its way toward the load. We know what the propagation velocity of that is going to be. It will be V sub P equals 1 over the square root of LC, where L and C are the inductance and capacitance per unit length of the transmission line. And so if you know the distance of the transmission line, let's say it's 3 meters or 10 centimeters or whatever it is, if you calculate the propagation velocity or speed, then you know how long it's going to take for that wave to get to the other end. The question is, what does it get there? What happens when it gets there? And that's where we're going to see the beginnings of a reflection process, where the wave is going to get there. It could possibly reflect and come back. When it reaches the source side, it will reflect again, and there's going to be a back and forth ping-ponging game. Eventually, it's going to settle out to something that is very familiar. So I want to emphasize this right away. I suggested at one point that everything you learned in your circuits class was wrong. That was partially true. But if you take away the transmission line here and you say, okay, we've got VG, RG, and RL, you know how to figure out what the current and voltage across RL should be without the transmission line. All right. And so what's important to keep in mind is that the circuit will eventually get there. Right, you can guarantee if RG equals RL, for example, right, and let's say VG is 2 volts. Right, let me just draw this example. Let's say this is 2 volts, and this is 1 ohm and 1 ohm. All right, this is an easy thing to solve. You got a resistor divider, and resistor equals, so that 2 volts are going to split in half. So you're going to get 1 volt across each of those resistors. Okay, so you know that. I can guarantee you that this back and forth process we are about to embark on is going to reach this same steady state. It may take some time to get there, but it will get there. And in fact, this is a good sanity check to make sure that you're doing things right. Right? It's going to be converging toward this value. So don't throw away your circuit knowledge, but we're going to have to adapt it to adjust to this new reality of the process of getting there. All right, so let me get rid of these and let's move on. So let's consider what happens to this wave when it reaches the load. And we're going to start out with a simple case of what if the load is an open circuit, right? There's no load, there's no resistor. It just ends with 2 wires that stick out and a big bowl of nothing. All right, so let's go back to the model for a transmission line. And the model was, we've got an inductor and a capacitor in each branch. And this branch repeats over and over again. And so I'm going to draw this a few times so you can visualize, right? In a real transmission line, using on actual inductors and capacitors, this is all shrunk down. Every segment is incredibly small, but every finite length of transmission line has an inductance and a capacitance associated with it. Right, so this is an L and this is a C. And we're going to start out with a wave that's coming in. And V in is going to be that voltage wave that's working its way down this transmission line toward the load. Right, and let me start out with the example of we have an open circuit here, right? So the transmission line just ends. The basic relationships that we have at our disposal are V equals L times DI dt. That is the equation that tells us how an inductor converts voltages into current after some delay. And we have the same for the opposite for a capacitor, that I equals C times the derivative of voltage with respect to time. A capacitor will convert current into voltage, but only if you wait a little bit for that process to happen. All right, so what's going to happen, right? Remember, we've got this V in right here, and we've also got a current associated with it, I in, and we know how those two are related to each other, that V in over I in must equal to the transmission line impedance Z0. All right, so this current here, I in, is flowing through this inductor. And you've also got this voltage over here that's established. Now this Vn has to go through one of two places. It can either appear across the inductor or it can appear across the capacitor, right? We can apply Kirchhoff's voltage law that this Vn, if I take this branch like that, I've got to get the same voltage drop Vn. So I've only got two choices where that voltage can go. And we know that inductors do not allow current to change instantaneously, but it does allow voltage to change instantaneously. Whereas capacitors are the opposite. Capacitors can accept a instantaneously changing current, but not a voltage. So initially, this voltage will appear entirely across the inductor, right? So we're going to get this voltage drop across the inductor. The inductor, the moment you put a voltage drop on it, invariably is going to have the current start to rise, right? It's going to have a non-zero di dt. So we start to get a little bit of current across this inductor. This current is going to start to flow because it doesn't want to go through the next inductor. It starts to flow through this capacitor. And then a capacitor, when you flow current through it, starts to charge up. It starts to build up voltage. So as we get a little bit of voltage building across this capacitor, the voltage across the inductor starts to shrink because remember, the sum total of those two voltages has to be equal to Vn. So as the capacitor charges up, the inductor starts to lose its voltage and therefore its current is not increasing as fast, and so it steadies out, and eventually you get this Vn appearing across the inductor, and you get the next current In appearing on the next branch. So that process keeps going, and eventually you're going to get this Vn appearing across this capacitor, and a current In moving this way at this junction right here. All right, but here we got a problem, because there's nothing else. There is no next capacitor where this can appear. So you've got this voltage sitting right here. And so what is going to happen, right? Think about this for a second, then I'll try to walk you through this situation. You've got this voltage across this inductor, you've got this current going through, and nothing at the next branch. All right. So think about this if you want, pause the video, but let me give you a little bit of a background here. In previous branches, there was another inductor that was capable of accepting this voltage right here. And there was a capacitor that was capable of accepting this current. In this case, though, there is no voltage and there is no capacitor. And so this current right here, this In, it keeps flowing through this capacitor, right? There is nothing else to divert it away. So we're going to start shoving way too much current into that last capacitor, that last little bit of capacitance. As a result, we're going to overcharge that capacitor. And it turns out, if you work out the math, we're going to overcharge it to a value of 2Vn. Right? We're going to double the voltage compared to what we thought would be the case, compared to the value of the voltage that comes in. Right? We had 1 volt, 1 volt, 1 volt, 1 volt, 1 volt, and all of a sudden, we just kept pouring that current into that capacitor and continued to charge it up because nothing could continue down that transmission line. And so we got 2 volts instead across this last capacitor. All right, so we got this 2 volts, but we're not done yet, because the moment that I've got this 2 volts, now I've got positive 2 volts right here, and I've got this node at 1 volt. And so look what's happening. Right now, I've got a negative voltage that is sitting across this inductor. A negative voltage is going to lead to a decrease in the current. Right, so we've had all that work to charge up the current on this inductor. And now that extra voltage appeared across the capacitor and sends a negative voltage going back through the inductor. And so the current on this inductor is now falling again. Right, that if we look at the current right here, it's going to have risen up right there. And now it's going to fall right back down. And it turns out it falls back to 0. Right, so this current eventually is going to disappear. And once this current disappears, what's going to happen is this 2 volts, because there's no more voltage across this inductor, that means that this 2 volts is going to have to appear right here as well. And so you can see that something has happened. We had 1 volt coming in, and it countered this end. There was nowhere else for that current to go, so it overcharged the capacitor and charged it all the way up to 2 volts. And now we have what seems to be a wave going backwards that's charging this capacitor up to 2 volts. And now this one is going to be charged to 2 volts. and etc. As that happens, these currents are also being killed one after the other. So we end up, after this wave comes in, hits the load, there's a reflection, it comes back, that both doubles the voltage and wipes out the current at the same time. Now that kind of makes sense for an open circuit, right? Because in an open circuit, we can't have any current, right? There's not going to be any current right here, right? I equals 0, but we can have all the voltage we want, right? This voltage is fine, no problem there. And so this seems to have established something where this reflective wave was necessary in order to both satisfy the boundary conditions where we have to have no current and only voltage, with the fact that the transmission line forced the V to I to be a certain ratio. This reflection was the only way to make everybody happy. Now, in terms of characterizing this voltage reflection, we're going to establish something called the reflection coefficient. Right? So we had 1 volt coming in, and coming backwards, we had a V reflected. I'm going to call this V out, which was also 1 volt. So we're going to define something called gamma. Capital gamma, this is very important. We're going to be seeing a lot of this. This is called the reflection coefficient. And for the case where we have an open circuit, we're going to define the reflection coefficient as V out divided by V in. It's the ratio of the voltage that comes back out to the voltage that comes back in. And it turns out for this case, this seems to have a value of +1. Since we set 1 volt in, and the reflected wave was another 1 volt that added a 2nd volt to charge up all those capacitors. So our value of gamma for this case, for the open circuit case, is +1. All right? So hang on to that thought. And let's now consider the opposite case, where we have a short circuit for the load. All right, so here's our inductor, here is our capacitor. All right, we repeat this process. I'll draw one more branch, and the load is a short circuit. Right, so here we go. We have added a short circuit that effectively kills this last inductor. So what's going to happen in this case is we've got current that's going to run through right here, right? That last voltage right here, right? Vn equals 1 is established on this node, and we got a current here that's established. Now, ordinarily, this current would come and flow through this capacitor and charge it up. Okay, but in this case, it can't because the capacitor is short-circuited. So the capacitor is not allowed to have any voltage on it, which means the current here is not going to flow through the capacitor, because if we put current through a capacitor, we must be changing its voltage. And changing the voltage of the capacitor is not allowed because it's connected to a short circuit. All right, so what is going to happen is this current is basically going to, keep pumping through, right? It's not gonna have anything to shut down that current, and so this current is going to double, and this voltage will remain at 0. All right, so we had an ion right here. Let me back up a bit. All right, so we have this incoming voltage that's established. And the reflection is basically going to be another voltage, an I in, that's established right here, and is going to cancel out the voltage that had appeared momentarily on this next to last capacitor, and that cancellation will move onwards. So this appears to be the opposite, in that we had 1 volt that was sent out to the load, and the load says, I'm not allowed to accept any voltage, so the only way to make the load happy, while also obeying the transmission line need to have voltage and current have the same ratio, is to launch a negative voltage back in the other direction. So in this case, we can say that gamma, the reflection coefficient, which equals to V out over V in, will be equal to -1 divided by 1, or you have a reflection coefficient of -1. We sent in 1 volt. That 1 volt charged up the capacitor one after the other on its way to the end. And the load said, nope, no you don't, no voltage here. And we sent back a -1 volt that wiped out all the charge capacitors. It, by the way, doubled the current, right? This IN added up over here, so we ended up with a double the value of the current along the whole transmission line as that wave went in the other direction. But when we talk about reflection coefficient, we're specifically referring to the voltage reflection coefficient. I'll get to in a few minutes what happens for current, all right? But this is specifically for the voltage, all right? So with that, hopefully that establishes the idea of the load has a certain need for voltage and current, and it has to have a certain ratio to it based on whatever resistance is there. And the transmission line also forces the voltage and current to have different values, to have a certain ratio to it. And the only way to make the load happy and make the transmission line happy was to launch a reflection going back the other way. So how can we solve this mathematically for the case where we have any resistor? All right, so let's consider this scenario where we've got a transmission line that terminates with a resistor. That resistor has value RL. We have a voltage in and a current that's coming in, and we might have a reflected wave or V out, and it also has a current I out. All right, so let's write down things we know. Things we know is that the load voltage will be equal to the current on the load times the resistor on the load. We know that, right? What else has to be true? We also know that the ratio of V in to I in must be equal to the transmission line impedance. And we know that the same is true for the reflected wave, that V out divided by I out equals Z0. Now the derivation is in the notes. I won't go quite through it here, but if you combine these three equations, solve for each other, and rearrange, and try to figure out what is the ratio of V out to V in, here's what you get. You get that V out over V in equals RL minus Z0 over RL plus Z0. This is definitely something worth memorizing. Again, this is the voltage reflection coefficient, usually denoted with a capital gamma. And it works out to be the load resistance minus the transmission line impedance divided by the sum of those two. All right. This, again, is for voltage. If, by the way, you want to know what the reflection coefficient is for current, I'll save you the trouble of solving for that. It looks like this. I out over I in is going to be the negative value, right? It ends up being the negative value of gamma. So if your voltage reflection is +1, then your current reflection coefficient is -1. It's the opposite. It's the negative value of it. And that kind of makes sense because in the short circuit case, where we had to launch a reflection that canceled out the current, we ended up doubling the voltage. And it was the opposite. It was an open circuit. We doubled the voltage, but we killed all the current. And so the voltage and current kind of have the opposite reflection coefficients from each other. All right. Now, if the resistor is anything other than a capacitor, anything other than an open or short circuit, then gamma will have some value in between, right? So gamma is always going to fall in between -1 and 1. Right? -1 is going to be less than or equal to gamma, which will be less than or equal to 1. Right? Gamma is going to slide in between that range. 1 means it's an open circuit on the load. -1 means it's a short circuit. And anything else is somewhere in between. Now notice, by the way, that gamma equals 0 occurs when RL equals Z0, right? When the value of the load is the same as the impedance of the transmission line, there is no reflection, right? Because the wave is carrying voltage and current at precisely the exact ratio that the load resistor wants, right? And so there isn't a need for a reflection to keep everybody happy. So this special case where the load matches the line, we're going to call this matched, right? When we have no reflection coefficient. All right. One thing that's worth noting, by the way, is if the intensity of the reflection coefficient also tells us something about the quality of the match. And let me give you an example. Right, let's say that Z0 is twice the value of the load resistor. Right? If you plug that into the equation, you end up being able to solve this, and that implies that the voltage reflection coefficient is -1/3. Right? Let's say we take this 2 and we flip it upside down and say that Z0 equals 1/2 times the load resistor. That works out to a value of gamma of +1/3. Right? So the absolute value of gamma basically tells us something about how far apart in like multiplication the load and the line are from each other. And the sign basically tells you which one is bigger and which one is smaller. Right? A positive value of gamma tells you that you're closer to an open circuit. Right? Closer to an open circuit, that means the load must be bigger, right? And that's what this is, right? Load is bigger. Right? A negative value of reflection coefficient tells us we're actually sort of closer to a short circuit case, right? That means the load is smaller. If the load is smaller than the line, that's kind of on our way toward being a short circuit. So this is load is smaller. And when I say load is smaller, I mean it has a smaller resistance compared to Z0, compared to the transmission line impedance. All right. So that is one big piece of this, but the other thing that's going to complete the picture is, okay, so I've got a voltage wave that comes in and it counters a load. If the load is not matched to the line, I'm going to get a reflection. It's going to go back toward the source. Right? So what's going to happen when it gets to the source? Right? So let's draw that and consider that case. Then we'll sort of have all the pieces together. Here is the line. Here's VG. Here's RG. Here's a Z0, and here we have this reflected coefficient, this reflected voltage coming in right here, right? Next question to ask is what's going to happen to that? And we're going to have essentially the same thing occurring again. There will be a reflection. I'm going to draw it with this little looping arrow right here. And I'm going to denote this with a gamma G, right? A reflection coefficient at the generator. And the reflection coefficient at the generator end will be equal to essentially the same equation that we had before, right, up here, except instead of the load being RL, the load is RG, right? It's the generator resistance that kind of acts like our load. So this reflection coefficient at the generator will be RG minus Z0 over the sum. And if you want to complete this picture, I really should put an L underneath this gamma, right? Because this is the reflection coefficient at the load, right? And so now you can see that I've got a reflection coefficient at the source, at the load side, and a reflection coefficient at the generator side or the source side. And if neither side is matched, right, what happens is I'm scaling the voltage by some number. Let's say it's a half, right? So I launch a 1/2 volt. It reflects with the reflection coefficient of a half and becomes a 1/2 volt. Then it becomes a quarter. Then it becomes an 1/8, right? I'm assuming that it's half on the other end too. And you can see that the voltage is getting smaller, but it never completely disappears. But with enough ping pongs back and forth, it's going to settle out. And the magic is that this will always approach the correct solution to the circuit that we would have anticipated from basic circuit theory. It just gets there via this back and forth process. It's kind of magical if we think about it, because I haven't told anything that that the generator needs to produce a certain current and voltage in order to supply it to the load, but it's going to get there if you give it enough time. So let me try to give you a visual for this, right? And I've got a little simulation software called WinTLS. This is available for you to use as well. And you can set it up to simulate different kinds of transmission lines. I'll be using it a bunch of times in the first half of this course. And so here is a basic transmission line. You can see there is a 1 volt source. There is a source resistance of 50 ohms, a transmission line impedance of 50 ohms and a load of 50 ohms. So this is kind of a perfect scenario. Everything is matched. You're matched on the generator side, you're matched on the load side. And so when I press this simulate button, what you're going to see is this plot down here is going to show the voltage as a function of length along the transmission line. And we're going to see this evolve with time. So let me just show you this real simple. I'm going to simulate here and going to stop it in the middle. And this, you can sort of see, this represents a wave that's clearly moving from the generator toward the load. You can see that this is 1 volt. The 1 volt is equally divided between the generator resistance and transmission line impedance. So there's going to be a half a volt that is propagating to the right. All right, and so I'll keep this going, continue. And when this voltage reaches the end, the reflection coefficient at the generator side is going to be 0 because we have a 50 ohm match between line and load. And so when this gets to the end, that's it. There's no reflection. Our circuit is basically done. We have already hit a steady state right here. And even though there continues to be voltage and current flowing from the generator toward the load, it's basically stopping there. It's not turning around and coming back. All right, so that's the simplest case. Now let's consider what happens when things are not matched. So let's make the load here into 150 ohms. All right, and I'm going to simulate this again. So at this moment, nothing has changed, right, from our original simulation. We got a half a volt working down the transmission line, right? Remember, the battery has no idea the load resistor is now 150 ohms. All it sees is a 50 ohm transmission line, and so it supplies a half a volt as a resistor divider between the generator resistor and the transmission line resistor or impedance. All right, so here we go. This wave is going to get there. Now, something very different is going to happen when this wave reaches the end. All right, so let me stop right there. Let's stop and think about reflection coefficients for a second. All right, we've got a load of 150, and we have a line of 50 ohms. And so if I plug that into transmission line formula, 150 minus 50 divided by 150 plus 50 is 1/2. So I have a reflection coefficient of 1/2. So I got a half a volt that's coming down this transmission line. It encounters this load. And what we expect is a half a volt signal to reflect and go backwards the other way. So let's see this. I'm going to step through one little step at a time. And there it is. Right? That is a reflected wave. The only way to satisfy the requirement for the wave to have a certain voltage to current ratio and for the load to have a certain voltage to current ratio is to have this reflected wave. So let me now continue this. And what you can see right here is that the reflected wave builds on top of the wave that's coming in. That half a volt is still working its way from the transmission line. It's like a steady stream of water that does not stop. And when this water hits the load, a new wave of water builds on top of what's coming in. But they're still adding up together. And so we take this 1/2 volt that's coming in there, and we add another 1/2 times 1/2, or a 1/4 volt built on top of it. So this voltage right here on the load is 3/4. It's the 1/2 that came in and the 1/4 that got spit back out. All right, so let's continue this. And right before this reaches the source, I'm going to stop it. All right, so we got this half volt wave that went out. A quarter volt wave is coming back, and this quarter volt wave is now reaching the generator side. When it gets there, it's going to see a generator impedance and a line impedance that are the same. They're matched. So in that case, the reflection coefficient at the generator is also 0. So we expect this wave, when it hits the generator, is going to stop, and that'll be the end. So let's play this and just make sure that that happens. There it is. We're done. We have 3/4 of a volt that now appears across the entire transmission line. We've reached steady state. The load has its 3/4 of a volt, and we have the correct voltage established everywhere. Right now, let's think about that for a second, because if I go back to the resistor divider rules, if there were no transmission line here, If I just gave you a battery, a 50 ohm resistor for the generator, and a 50 ohm resistor for the load, and I asked you what's the voltage on the load, you would say, oh, well, of course, resistor divider rules, that's 3/4 of a volt. Hey, that's exactly what we have established, despite needing this back and forth reflection. All right, now let's complicate the problem a little bit more, and let's make the source be just 10 ohms. Let's make it pretty small, right? People like to do that. You'd like to have voltage sources that have pretty small resistances, so let's try this and let's simulate and watch what happens, right? All right, let me just stop right here for a second. Notice the voltage that has started out on this transmission line is higher than it was before, right? It's actually 5/6 of a volt, right? Because again, we've taken this 1 volt and we've resistor divided it between the 10 ohms on the generator and the 50 ohms on the transmission line. And so 5/6 of a volt is working its way down the transmission line. Let's keep that going. We're still going to have a reflection coefficient of 1/2 when it reaches a load. And so there's the reflection right there. It builds on top. All right. I'm going to stop this right before it gets to the end. All right. Now we now have a reflection coefficient that we expect on the generator side. And that reflection coefficient is going to be negative, right? Because the generator resistance is smaller than the line. And so we're going to get a negative reflection, and let's see what that looks like. All right, so here comes that wave is reflecting. So that reflection coefficient here, let's think critically about this, right? The reflection coefficient with the 10 ohm generator and a 50 ohm line is 10 minus 50 or divided by 10 plus 50, right? So it's minus 40 divided by 60, it's negative 2/3. So the reflection coefficient at the source side is negative 2/3. So ask yourself the question right now, what voltage is going to work its way back in the positive side after this reflection? Right, so we know that 2/3 is going to be there, but what are we going to multiply it by? Our two choices are, it's going to be the entire voltage on the transmission line, or it's just going to be the voltage of the reflected wave only. So think about that for a second. Pause the video if you'd like to. Okay, so this is the important part. The reflection coefficient only applies to the wave, the actual moving wave, not to the entire voltage. So we would take this value right here, just the extra voltage that has reflected and come back. We would multiply that by negative 2/3, and that will be the value of the new voltage that will work its way back toward the load again. So let's see this, see what that looks like. There is a negative reflection coefficient. You can see this is now a negative wave. It's going to lower the transmission line voltage again. So let me just continue this. And in fact, I can speed it up. So you can see that this can go on for a while. In fact, in principle, it goes on forever because this voltage wave is getting smaller and smaller. Each time it bounces, it gets multiplied by a number that is between 0 and 1, right? So it's getting smaller. And eventually this is going to settle out, but it will take some time. When it settles out, it will always reach the value that you think it should. And by think it should, I mean you can take 1 volt, do a resistor divider between 10 ohms and 150 ohms, and that's a value that is eventually going to be established if we wait long enough. And in fact, you can take a look at this and you'll see it is almost a volt, a little bit less than a volt, and that's exactly what this line shows. Each tick mark, by the way, is a 1/2 volt. You can see that shown over here. Tick mark equals 0.5 volts. All right, so this seems to be some weird technique that gets us to where we expect it to go, but it takes a little bit of time. But this is important because if you are standing with the voltmeter at the load and you're measuring all this, it doesn't jump straight up to its value. There clearly is some up and downs as it gets there. And so taking us back to the very beginning of this lecture, I talked about this idea of ringing. At this point, you can hopefully see how this ringing can occur. Because if I have reflection coefficients on both ends that are correct in a certain way, we'll get to that later, then we're going to get this back and forth over and over again, right? Too big and too small, and too big and too small, too big and too small, and eventually it settles out because, again, those reflections are being multiplied by a number that is somewhere between -1 and 1, or has an absolute value that's less than 1. All right, so there's one last thing I want to say, which is that you can also go backwards, meaning you can figure out what the line to load ratio is if you know what the reflection coefficient is. And that formula is in your notes, so you can take a look at that, but you can go backwards. All right, in the next video, we're going to talk about a sort of visual way to keep track of all these back and forth reflections, and we'll do a little example so we can see it in action.